Hi, I'm DJ Ware. On this episode of the CyberGizmo, I'm going to be taking a step back in time and kind of looking forward a bit from the lenses of when I started, and talk about some of the things that were going on, and then some things that happened, some bad things. Anyway, right after this. So what I wanted to do today was to, like I said, take a step back and talk about the future of automatic computing machines. That's what they were called back then. And this is from a perspective when I actually started working with computers, was in 1974. So we had a thing that happened about 9 years earlier, Moore's Law, which said that every 18 months, 2 years or so, computing would double. So the number of transistors would double on the chip, and by that we would have faster processors as a result. And that remained very true all throughout the 70s and 80s, 90s. So yeah, it worked out pretty well. You probably remember this machine. This is the IBM 701, and it was a higher level language machine, but it also did some of the more traditional things. In the old days, and this would be around 55, in the old days, we programmed using binary. I've only done this once. I wrote a binary program one time. One time. It's not fun. But I did it to diagnose a hardware problem. But we had to go through and enter the actual binary instructions and sequences into the machine. It was painstaking. It was one word at a time. This one, then this one, and this. You just enter them sequentially, and if you messed up, you had to erase it. And if you messed up way back here, you had to erase all the code in between. So yeah, it was pretty tedious to do, and usually people planned that out on work tables before they entered them. But then somebody came along and they came up with the assembler, which was I could write those instructions and the assembler would create the binary for me. So I could deal with it in kind of a pseudo-English and a pseudo-language that I could then understand, and it would help me go back and understand what I did, because if I was looking at numbers, I would have to go get the books and figure out what things were actually going on. But in the assembler, Once they came up with that, they showed it to the people over here doing binary programming, and they went, "No, that's not programming. Go away." And they just didn't get it. They didn't understand. I mean, first, they didn't want to change, and second, I don't understand that. It doesn't make any sense to me. That's not programming. In fact, I remember a story about one of the professors had a class of students that were working on binary code, and one of them decided to try the assembler to write his program, and the professor found out about it and scolded him for it. How dare you take up precious computing time by writing a program to write your program? That's ridiculous. You shouldn't be using it. So that's just the way people react sometimes. In 1957, John Backus came out with formula translation, or Fortran. And this was the first time we could actually write loops, and we had statements and variables that didn't depend on memory addresses, and you could move things around, you could reprogram them. It was pretty easy to understand, but these guys back here on the assembler side didn't like it. They were like, "Oh, that's not fast enough. You're not close enough to the machine. Those high-level languages are junk. Go away. We don't want it. We don't understand it. We don't get it. What would I need that for? Leave me alone. I'm doing fine. This machine is going to run great. It'll run forever." But the problem that you had with assembler and also binary is it was tied to a specific model of processor. Even IBM didn't stay with the same instruction set on every processor they sold. And so, yeah, you ended up having to dump your programs and rewrite them if they were written in binary. If they were written in assembler, you could probably translate them, but even then, the instruction sets wouldn't be necessarily the same. But anyway, in 1972, Dennis Ritchie wrote C, and we know about that. We use that today, and wrote this as your first program, probably the hello world, which, by the way, is the assembler and the binary in Linux. So, but this kind of programming language is single instruct. I mean, then the processor is going to take the instructions off one at a time, and it's going to execute them. It's going to get the next one, and then it's going to branch or loop, or it's going to fetch some data, or it's going to store some data off. But that's basically, it's going to do these things one at a time. And but Ivan Sutherland had a little bit different approach to programming. He didn't want to take the time to explain to the program, here's exactly what I want you to do. I'm going to draw on the screen, and what I want you to do is to do two things. I want you to make sure that all the lines I draw are parallel, and if there are any intersecting lines, make sure that they are at 90 degrees. That was the two goals he gave the program. He didn't describe to the program how to do it or what specific functions to do. He just said, here's the goal. I want you to make sure the lines are parallel and make sure the lines are intersecting at 90 degree angles. And so he could draw on the screen and then hit a button on there's a pad of buttons on the screen here. There's a demo on YouTube if you want to watch this. Watch him go through it. It's it's over 55 years old, 57 years old now. But yeah, it'll go through, and then you can see that he draws on the screen kind of sloppily. Like down here, he's drawing a rivet, and he's got it tilted, and he's got the lines he's got them in a out of kilter, and then he just pushes the button. The program comes up with that. So he had to direct it to the axis, about where to rotate it about its axis, but it figured it out on its own. So I mean, that's the kind of programming tools they were working on back then. There was another one called GRAIL, and this one was on the RAND tablet. Yeah, it's a tablet. It's right in front of him. It's pretty big, but it is a tablet computer. So you thought you had something new, didn't you? But it looks like all he's doing is drawing flowcharts, doesn't it? It looks like he's just flowing out, but he's not. He's writing a program. And he's using flowcharts as the symbology to do it. So everything he's doing here, there are some instructions in code up here that's being generated from all this stuff that he's working on. And he can erase, he can move the lines around, and the program will rebuild itself. And then when he's done, he has something that will execute and run. But he didn't have to spend time in front of a screen going through reams and reams of text in a column, in a row, looking down through all of it and trying to figure out, did I have the right brace here, the right semicolon there? And did I comment enough so that someone can follow this code? I mean, you could look at that and you could see exactly what kind of things that was going on with it. But the reason why those two languages were similar was they were manipulating data instead of the program manipulating the code. Or manipulating the hardware. It was actually manipulating data to do things. In 1968, Douglas Engelbart gave the NLS online, which was called the online system. It was also known as the mother of all demos. And during this, I think it was about 90 minutes or so, he showed some really groundbreaking things that no one had ever thought of before. First, being able to use a device called a mouse in order to interact with a video display. That was totally foreign. No one had even thought about that. Before that, they were using light pens on the screen. But he showed copy-paste. He showed find and replace, full screen editing. He showed being able to manipulate text and how to reorder it, how to move it around, how to make it, how to apply goals to it. And he went on that. If you get bored, and you want to see some really amazing old tech, it's a pretty good demo. It's also on YouTube. You can see that there. There was also a couple other programming languages, and I'm going to say that regex, even though it's not really a programming language, it is a pattern matching. and it does have a syntax. But the Snowball was really more complete but it wasn't regex. It was different. Snowball started out in 1962, and that was done by David Farber at Bell Labs. It was a text processing language. It was a language strictly to manipulate text. It could analyze strings. It could do manipulation of the strings based on what it learned. And there was a bunch of offshoots. I think the compiler was called Spitball, and I think there was Snowcone that was some output thing. But there was all kinds of spin-offs to the Snowball, and the 69 regular expressions talked a little bit about that in GREP, but didn't really probably take it far enough. The purpose of regular expressions is so that when you want to search for something, how do we do it in programming? What's the first thing you think of? Writing a parser, right? I got to go through and I've got to parse this text. No. Regex would be the first thing you're thinking of because regular expressions is faster. It's more efficient. But if you use, and it, of course, was built on this new thing called Unix back then. There was another set of programming which are goal-oriented. Planner, which was Carl Hewlett from MIT, invented Planner. And it could take things like, here's the procedure, and it would come up with the goal. Or give it a goal, and it would come up with the procedures to reach the goal. So pretty advanced stuff. There was also Prolog, which in the early days of artificial intelligence work was used quite a bit. Lisp had been around a long, long time. Lisp comes from mid-50s, somewhere around in there. So, yeah, if you think Richard Stallman wrote and invented Lisp, Richard Stallman was barely out of diapers when Lisp was written. So, it took goals and it just did the backward side, goals to procedures. So one thing that early programmers used to do is they would say, God, why can't this program do what I'm thinking it should do instead of what I told it to do? And that's what those two programming languages were designed. That's what they were all about. Sorry about that. Dry throat. Okay. Yeah. One of the other ARPA projects, they funded a lot of the early computer research. And there was, I don't know how many spin-offs that came from it, but one of the things was J.C.R. Licklider. I've talked about him before. He wanted to build a worldwide network, and he knew that engineers were going to under-deliver. So there's a memo. I'll put a link to it in the show notes. It was called Intergalactic Computer Network, and it would always write to the responsible people of the Intergalactic Network, and then he would go through his thing as what he was trying to do. But what he was trying to do was to come up with a global network in which all computers could be hooked into it. But all 1,000 of them at the time. But he knew that but this would cause a problem. And the problem it would cause is the communicating with aliens problem. It wasn't because he was trying to communicate with aliens in outer space. What he's referring to is computer programs were going to have to learn to communicate with one another in order to figure out what services were being supported by one and whether or not it could use those services to do something that it needed to do. But the machines would have to figure out how to do that on their own. And the programs would have to figure out how to do that on their own. So how do we solve this today? How did we solve this problem? We went out and we generated APIs. We, the programmer, went out and told the machine, this is how you are going to communicate. You've got to follow this blueprint. It's got to have these exact fields, this exact message, this exact protocol. And what you did was you locked the two programs together tightly. It's called tightly coupling. And they can't move from one another. The programs are done. They're stuck. And if one of the programs changes the API, guess what? It's so brittle it falls apart and it breaks. But the idea of that, what Licklider was talking about in the communicating to aliens problem, is instead of fixing that interface and locking the programs into it, you made them learn about each other, and then they were free, even though they knew about other programs that were running and what services they were running, they were also free to look for better ones. So if you, in the, I know this is a sci-fi novel, but if you want to figure out what I'm talking about, in the Colossus series of sci-fi novels by Dennis Feltman Jones, he showed a possible way that computers could discover similar features and functions about another computer. It's when they put Colossus, which was built in the U.S., online. They connected it to the network, the Intergalactic network, and they connected it to the network. It discovered a system that was just like it. It had the same features, same functions, and it was in the USSR. It was different. I mean, it wasn't programmed exactly the same way, but it was goal searching and the same kind of thing. It was called Guardian. And the two computers are trying to figure out how to communicate with one another. And so they start sending math problems. They start sending math laws and binary, and they're counting up in binary, and they're sending factorial numbers, and they're sending primes. And finally, they figure out a language that they can use between the two of them to communicate. And they combine anyway. It just, if you want to know a way that might work, it was pretty well thought out in the book. But today we call the Intergalactic Computer Network the Internet. The other thing that in the 60s that was pretty important was real-time response. So we didn't want lag. We didn't want things to wait and be slow and take their time. And we wanted it instant. We wanted it bang. I want it now. I want it right now. So, and I don't want to wait for it. I don't care how many users are on the system. I don't care if there's 1,000 users. I want my answer right now. And we don't have that problem today, do we? We don't ever have lag or have to wait on something, or it's real slow and we're thumbing our fingers around going, wow, this could have been, I could have had coffee while I was waiting for this to finish. That doesn't happen today, does it? Nah. Anyway, but we wanted several different ways to interact, and I'm showing Play-Doh here to interact with them. So we wanted to show different ways of interacting with them. We had keyboards, touch screens, and in some cases on Play-Doh, there were some that were set up to do rudimentary speech. And also you could talk to it, it would talk back, so it would give you a response. But we didn't we had to figure out ways to do that. I remember there was a problem on one of the networks at the University of Illinois on Play-Doh, and it wasn't responding correctly. It wasn't working right. I don't know if it was on their system or whether it was on somebody else's system, and they were calling Dr. Bitzer to help with it. And Bitzer was a mathematician. He was a very sharp guy. And he's listening to the problem, and it's having latency. It's got problems. And he's thinking about it, and he's going, so the other end of the phone, they're talking about increasing the bandwidth. They need a bigger pipe. And Pitzer's thinking about it. He's going, no, you don't need a bigger pipe. The problem here is that you aren't using the channel well enough. You need to unthrottle it. You need to pick it up. You need to make sure that, it's the old adage. When you get the other end on the phone, tell them everything you want to tell them before you hang up. So that was what he was really referring to, was that if you get a connection to the other end, blow the requests all down the line at once, and then stop, and then gather up a whole bunch more, and then shoot them all down at once in a burst. So that was what he was talking about. And by that, he got rid of the lag. So, sometimes the problems aren't obvious to solve. That's the point. There's this new device that Intel developed. It's called a microcomputer. When I started in this business, a processor usually was a pretty big cabinet, and huge cabinet. And the smallest one I worked on had 25 boards in it. And I'm not talking about circuit boards like your motherboard. These boards were about 18 inches tall and about 3 feet deep. And there was 25 of those, and that included the processors, the memory, the logic, the controllers that did I/O, Also the thermals and some of the diagnostics that went on in the machine. All of that was inside of there. So it had all the channels and all that garbage. But this was the first time all that was really combined onto silicon. So, yeah, I mean, other than that, they had to build up these huge, huge cabinets full of stuff. So this really shrank down things for us, even though this was kind of a very small machine in comparison to what we have today. But that was definitely a breakthrough. Unfortunately, we have throttled ourselves with this, the von Neumann architecture, and we're still using this. For the life of me, just don't know why. It is a sequential processing model. In other words, the CPU takes an instruction, it fetches it, it decodes it, it executes it, it stores off some result. And I don't care how many pipelines you have in a machine, every instruction has to do those steps over and over and over again. And every time it fetches something from memory, it's got to wait. And memory is just going to sit there and go, well, I guess I'll wait for the next request because I ain't got nothing else to do here. But even though they're both the same, they're both transistors. I mean, the CPUs are made up of transistors. Memory is made up of transistors. But yeah, I don't know. It just sits idle for most of the time. So, I mean, the von Neumann architecture was great for a time when you had computers that were based on vacuum tubes or relays or that kind of stuff. And they used memory that was based out of core memory. It was wired together, had a ferrite core in between. And then they ran current one way and it became a 0, and it ran the other way, it became a 1. But you had that, or you had spinning disks. You had these large platters. I talked about that on the storage, one of the storage videos I did a long time ago. But anyway, this architecture doesn't work for us today. I mean, yeah, we still use this damn thing. I don't know. I don't know what's wrong with us. But I guess we're complacent. We like things that work, and we don't want to break things. We need to break things. This is the other problem, the thread locking model. Thread locking model goes back into the early days of operating systems. We used to call it send, receive. It is a thread lock. And it's one of the atomic structures of an operating system. But thread locking model is terrible. It's horrible. It's one of the dumbest ideas we've ever come up with. And instead of solving the problem of parallelism, we decided to make make it an artificial thing out of it. We mimic it. We use threading and locking to try to approach concurrency and fool ourselves into thinking that we've got concurrency when we don't. Because you have all these threads running and they're all protecting their memory that they're supposed to be sharing with the other guy, and they're locking it so the other one can't use it. So they sit there and look at each other for a while, then they take off and run for a while, then they look at each other for a while. That model just doesn't scale well. And it's the wrong way to do parallel programming. I mean, if you go back to the early days of Cray, when he was working on the barrel shifter and he was working on the Cray 1, he solved the problem. It's already been solved. What are you messing around with this stuff for? This is dumb. Anyway, but there was, at least from a hardware standpoint, it's been solved. From a software standpoint, I think we still got a ways to go. And Carl Hewlett, same guy that invented Planner, came up with an idea called the actor model. And he came up with this I think this was back in the 70s sometime. But this was a potential solution to the thread locking problem. So what he did was he borrowed something from physics, and this is kind of the way the atomic structures link together in forming materials and us and everything around us. But basically, an actor is a fundamental unit of processing. So each one of these circles out here is an actor. And within that actor, you have processing and self-contained. And you also have some storage, and you also have some communication channels that are inside that actor. So the storage is used to do computation on data, but it's also used to persist things that need to be persisted in case something like when I'm done or I need something, I'm going to have to send a message to another actor that's out running in the system so I can get the stuff that I need to continue. So each actor can have one or more addresses, and that depends on how many people are calling. You see a triangle here. We got two. Each one of these have 2 addresses, right? So the axioms that Carl Hewlett set down were: a actor can receive a message and process it, single thread. Can't do anything else until that's done. If you want more copies of it, you want to parallelize it, go create more actors that do that same task. That was his premise. Second, creates additional actors, including replicas of itself. The replicas of itself were to be able to anticipate. So I could send a message to myself and act like this, and he calls it the future, the future actor. So I'm sending a message to the future actor to tell it to do something, and it sends. So the third thing is it sends to actors that it knows about. So it has to learn about them before it can become communicating. So before it can start communicating with them, and then the fourth thing is that there has to be a designation to how to handle the next message that it gets. So in other words, that I have to either I'm anticipating that because I made a request for data, I probably am waiting for that data to come back, or I'm waiting for an acknowledgement because I sent off some data to somebody that made the request, and I'm waiting for an acknowledgement to come back that they got it. And then I can then clean up my local persistent store because I know, okay, they're done. I'm done with that data. I can go move on. And the other thing is you can process out of order messages because you don't really care. There'll be something at the end. MPI, the massively parallel systems, they all handle this today already. They handle things out of order, and there's usually something at the end of the collector to say, oh, have I gotten everybody's answer back? Are all the scores in? Am I done? If I'm done, it moves on. But if it doesn't have them all, it's probably going to go, hey, Joe, how come you don't have this done? Send me this stuff. Yeah, so I'll put some links below that'll further explain it. There's some videos on this too that Carl teaches. So yeah, if you're interested in that. So where the heck, why did all these ideas come out in the 60s and 70s? What was going on back then? Yeah, well, you know what was going on back then. But that wasn't it. It had nothing to do with it. What came out of it was computers were finally starting to reach a point where they became powerful enough that you could start doing stuff with them. Yeah, it was expensive. It'd take a lot of money to do it, but they were starting to become powerful enough where you could actually start exploring some things with it. And people were putting video screens on these computers. And, well, that kind of ended the whole tape card thing because I didn't need that anymore. I could, if I wanted data, I could get it back on the screen. I don't know how long in my life I kept teaching people about using online computers, and they kept printing out stuff. It was like, why are you doing that? I don't want to lose it. You're not going to lose it. It's on the machine. But what if I need it again? Then request it again. I don't know. People they fall back into old habits all the time, and that's one of the problems that we have, is that we keep falling back into old habits that we have. But the other half of the things in the 60s were we didn't know. I mean, I was out of the 70s. We didn't know what we were doing. We were just we were given a problem. You didn't know how to solve it. We just figured it out, right? I mean, we go out and try things. Hey, let's try this. Let's try that. We don't know if this is going to work or not. We'll just try it. Today, though, everybody thinks that, oh, well, you've got to be doing it. It's like a religion. You got to do it this way or you're dumb. Or they'll punish you. If you're not doing it my way, you're dumb. And that's wrong. That's not because if you think you know how to solve the problem, you've lost the race. And you've lost the race because you stopped looking for a solution the minute you thought you knew how to solve it. And that's the problem. That's the problem today. That's the crux of the problem. Is because if we don't admit to ourselves we don't know what the heck we're doing, we'll never get beyond this stagnation that we're in. And we are stagnated. We are stagnated right now. We're stagnated on ideas that we were trying to avoid in the 70s. We went down the wrong road. Why? Why does always this happen? It happens because businesses direct us there so they can make more profit. I don't have a problem with companies making a profit, so don't misunderstand me. I have a problem when companies become monopolies and they start controlling things and they start directing things, and we end up in these cul-de-sacs, these dead ends that takes us years and years to dig out from under. And that's the problem that I see. And we've kind of perpetuated this problem in 2 generations of programmers so far from where I started. There's been at least 2, and they're teaching the same thing. And I'll bet you, I don't know if it's you young guys, I don't know how many of you have seen these kinds of things before or even thought about programming outside of doing text on a screen or allowing the program to figure things out. Yeah, you call it artificial intelligence. But again, you're following a roadmap. Again, you're following a roadmap. Artificial intelligence, I think, is a good thing. I think it's a positive thing. I just think that building it on top of von Neumann architectures with thread locking models is just dumb. It's really dumb. So what do we need to correct it? Admit that we don't know what we're doing, and then look for a new way to fix it. That's all I had for today. Hope you enjoyed this talk today. I'm not trying to punish anybody. I'm not trying to beat on anyone. I'm just telling you, that's how it is. That's how I see it. And that's a view from the past. And hope to see you all again real soon. And as always, please like and subscribe. Hope to see you all again. Bye for now.